I had a realization just now. Every single time I start a video, I'm pretty sure the very first thing I say is, alright. So, alright, let's talk about the solubility product and how it compares with the solubility, how they are different from one another. So, first of all here, the solubility product, it does not change with the pH or with the presence of common ions. So if you have a solubility product for a particular molecule, it does change with temperature, as we'll see, but if it's at the same temperature and you add a whole bunch of other stuff into your mixture, the solubility product does not change. The solubility does change quite a bit. The solubility of a molecule will change if you have common ions present. If you remember our discussion from the previous chapter, when we were talking about like putting in a strong acid into a mixture with a weak acid, and that strong acid will limit the amount of that weak acid that dissociates. It limits the solubility, so to speak, the amount of dissociation that can happen in that weak acid. The same thing is true here. If you put something in that has an ion in common with the molecule that is dissociating, that is dissolving, then the solubility of that molecule will change, but the solubility product does not change. Namely because the solubility product does not care where the ions come from. It only cares what the concentration of the ions in solution are. Like I mentioned a second ago, they actually both will change with temperature, the solubility and the solubility product. So the temperature does matter. And one thing here is when we're talking about the solubility product, we have to have a saturated solution. If we don't have a saturated solution, then there's no equilibrium to look at. If all we have is a little bit of sugar, for example, dissolved in water, well, sugar's not a good example, a little bit of salt. If we have a little bit of salt dissolved in water, and it is just a little bit, so all the salt is dissolved, well, then there's no solubility product because there's no solid. There's no equilibrium that is present. Everything is dissolved. We have to have a saturated solution. We have to have a whole bunch of stuff, in the case of sodium chloride, so that we have an actual solid sitting on the bottom of the beaker to be in equilibrium with the salt that is in the solution. So it has to be saturated. Otherwise, we can't do anything that we've been doing up to this point. So very similar to what we saw in the previous chapter, the common ion effect does come into play here with solubility type reactions, and it's pretty much in the exact same way that we saw before. So if one of the ions in a solution in equilibrium is already dissolved in the solution, the equilibrium will shift to the left and the solubility of the salt will decrease. So for example, again, sodium chloride, if we add a bunch of that to a solution that already has lead chloride in it, the lead chloride is really not soluble. It's actually, based on Chem 1 rules anyway, it is insoluble, but you can get a little bit of it to dissolve. But if you put some sodium chloride in there, that little bit becomes practically nothing. It will decrease the solubility of lead chloride very significantly, because you essentially put in a whole bunch extra of this with that sodium chloride. And if you remember Le Chatelier's principle, if you increase this by a lot, Le Chatelier's principle says the equilibrium is going to try to get back where it was before. The only way it can do that is to consume that extra stuff that you put in there by pushing the reverse reaction, pushing things to consume the amount of lead in solution to get back to the lead chloride solid. So if we take a look at an example here, we're asked to find the molar solubility of calcium fluoride. So we're trying to find how much of this will dissolve in a solution that already has 0.1 molar NaF. So calcium fluoride is not as soluble as sodium fluoride. It is still a little bit soluble, but not as soluble. we need to try to figure out what are the concentrations of calcium and fluorine in these solutions. The nice thing is we actually already know the concentration of the fluoride. So if you remember here, KSP for the calcium fluoride is going to be calcium 2 plus times fluoride squared, because we're going to have 2 of those. We actually already know fluoride, because the sodium fluoride here, this is completely soluble. All of that is going to go into solution. We're actually just flat out told that here. We're told that the concentration is 0.1 molar. So because we have 0.1 molar sodium fluoride, we also have 0.1 molar fluoride. Sodium, we couldn't care less. We don't care what it's doing. But the fluoride is what we care about. So the fluoride here is actually going to be 0.1. One thing that is not pointed out in this problem that you will have to do here is we are actually going to have to just look up the value for KSP for calcium fluoride. And I'm going to have to look that up on my phone, actually, because I don't have that right in front of me. So let me see here. So I am getting the KSP of calcium fluoride is 3.9 times 10 to the negative 11 is the KSP for that molecule. And you can feel free to look up the KSP as well if that's not the thing you're trying to find, obviously. If it's trying to get us to find KSP, well then don't just Google it. But if it's not given in the problem and you think you need it, go ahead and look it up. See what it is. And there's tables in the book as well. I just don't have my book with me right now. So KSP is 3.9 times 10 to the negative 11. So we can do a little bit of rearranging here. 3.9 times 10 to the negative 11 is equal to concentration of calcium times 0.1 squared. We just went ahead and put in the 0.1 here for the concentration of fluoride. That is going to be squared. So this is one equation with one unknown, the concentration of calcium 2 plus. If we go ahead and solve that, let's see here, 3.9 times 10 to the negative 11 divided by 0.1 squared. That gives us the concentration of calcium is 3.9 times 10 to the negative 9. Now, if you're thinking, but I don't want the concentration of calcium, I want the concentration of calcium fluoride, we need to remember, whatever the concentration of calcium fluoride is, because we only get 1 calcium for every calcium fluoride that dissolves, this is actually also the concentration of calcium fluoride. So that actually is our answer. 3.9 times 10 to the 9 molar is the concentration of calcium fluoride. And again, that's because it's a 1-to-1 ratio here. For every one of these we have in solution, we are also going to have 1 calcium. So it's the same number. If instead we had used fluoride, we couldn't do that because, again, we have a secondary source for that fluoride. We can't just take the concentration of the fluoride and say, oh, well, for every fluoride I'm going to have half that of the calcium fluoride. It doesn't work because we have 2 sources for that fluoride. We have the fluoride coming from our calcium fluoride, but the vast majority of it is coming from this. But we only have 1 source for the calcium. So however many calciums we have in solution, we had to have the same number of calcium fluoride molecules dissolved. All right, hope that makes sense. If not, we can talk more about it when we meet and discuss. But for now, let's go ahead and do another practice problem here. So this one says in the first step in the preparation of magnesium metal is the precipitation of magnesium hydroxide from seawater by the addition of lime, a readily available inexpensive source of OH- ions. So they give us the KSP for that reaction here. The concentration of magnesium 2 plus in seawater is 0.0537. will magnesium hydroxide precipitate when enough calcium hydroxide is added to give an OH minus concentration of 0.001. So our OH minus concentration is 0.001 molar. Okay, so the hardest part of this question is the working out how do I get from where I am to what I'm trying to find. So go ahead and pause the video here in just a second and try to figure out, given what I know here, I'm given the equation, I'm given the KSP value, and I'm given the concentration of both of these things, how can I work out if this solution is going to precipitate magnesium hydroxide? So go ahead and pause the video and think about that for a minute. Alright, so hopefully you paused the video there and you're back now with at least an idea, or maybe the answer, as to whether or not we will get magnesium hydroxide precipitating. The key thing here is to think about, what is the KSP telling us? So the KSP here, what this is saying is, in our solution, when we're at equilibrium, this number is equal to this in terms of the concentrations. That number, and actually I'll go ahead and just write that in here, so 8.9 times 10 to the negative 12 is equal to these concentrations, and one of them being squared. So if it's at equilibrium, these will equal this. So if we go ahead and plug these numbers in, because we have both of these, we have the concentration of magnesium and we have the concentration of OH minus. If we just go ahead and plug those in, let's see what we get. So we're going to have 0.0537 molar times 0.001 squared. And if we do the math here, what we get is that is equal to 5.37 times 10 to the negative 5. So we have to think about what this is actually telling us. This number, is it smaller or bigger than this number? Hopefully you said bigger. So this is significantly bigger. It is 7 orders of magnitude bigger than this number. So this number is telling us if we're at equilibrium. Okay, this is at equilibrium. These concentrations will equal this. When we actually plug our real-life concentrations in, it's much bigger. It's a much bigger number. If you remember what KSP is, that is products over reactants. That's what KSP is equal to. Because this number is way too big, what that means is that we are not at equilibrium, and even more specific than just not being at equilibrium, we have too many products. Too many products, too few reactants. Now I know that the reactants don't actually show up here, but just reducing the number of products will work as well. But we have too many products, too few reactants, so what that means is this reaction is going to shift to the left to consume the products. It has too many products to be at equilibrium. It is going to shift towards the equilibrium, and in doing so, it's going to move this direction, which will indeed make more of this. It's going to make more of the magnesium hydroxide, which will precipitate out of the solution because it is a solid. So, in this particular mixture, yes, we will indeed precipitate magnesium hydroxide. Alright, hopefully that makes sense. We're we're going to go ahead and move on to the last little bit here, and I think we're going to go ahead and just work our way through this. It'll be a little bit longer video for this one, but that's okay. We're going to talk about a few things that affect solubility. The first thing here is the pH. We mentioned before that pH affects solubility, but now we're actually going to talk about how it affects solubility. So if a substance excuse me, has a basic anion, it's going to be more soluble in an acidic solution, and substances with acidic cations are more soluble in basic solutions. The reason for this is if in this example here, we have lead fluoride, and it's really not very soluble in water. You can get a little bit of it to go into solution, but most of it stays as a solid at the bottom of the beaker. But if you put in an acid, so if you put in something like hydrochloric acid, so you're going to add H plus to the mixture. What happens with that H plus is it is going to go find the strongest base in solution. And the strongest base in that solution is fluoride. Now, if the fluoride had not been there, it just would have been OH minus floating around in solution. Or sorry, H plus floating around in solution. So it would have just been hydronium ion. But because we have that fluoride there, the H plus is going to find that fluoride and react with it to make HF. And so because the H plus reacts with the F minus to form hydrofluoric acid, now our original equilibrium, the equilibrium between the lead fluoride in solution and the lead fluoride in the solution, is now all messed up. Because the fluoride that was participating in this equilibrium is now gone. The fluoride's just disappeared. It can't participate in this equilibrium anymore, and so the solid starts to dissolve more to try and replenish that F minus in solution. Again, it's Le Chatelier's principle. You effectively took away the reactants, forced them to not be available for the equilibrium anymore, and so the solid begins to dissolve more to try to get those back to where they were before. And so having that basic anion caused it to be more soluble when you put in that acid, which essentially reacted with that basic anion. If, on the other hand, you have lead iodide instead, iodide is not basic at all. It is negligibly basic. And so if you put in H+, the H+ is not going to react with that. If it did, it would be making a strong acid, which would just go right back to being dissolved again, breaking apart again. So lead iodide is not helped. The solubility is not affected by the pH. Something else that can affect solubility is if you can form complex ions, and the process that's happening here is really exactly the same as the last slide. It's just a slightly different reaction that's taking place. So silver chloride is the example here. Very little silver chloride will dissolve in solution, but if you add ammonia to the mixture, the ammonia forms what we call a complex ion. The ammonia will complex with the silver, and as soon as it does that, the silver is no longer available for the equilibrium that was present before. The sodium is not able to go back to being a solid, and so just like before, Le Chatelier's principle then pushes the equilibrium to dissolve more of the silver into solution, and so just by adding ammonia, you're able to cause the silver chloride to dissolve because you've essentially pushed the equilibrium so far in one direction that you use up all of the solid that you had there before. So it's the exact same thing that was happening over here. You have a side reaction occurring that essentially removes one of the products from being able to participate in the equilibrium, and that pushes the equilibrium to dissolve more stuff. And so this is just a list of other complex ions that can form. There's quite a few of these. Usually these things that can react with a metal to help it to dissolve more in solution, these are called ligands oftentimes. And so you can get actually quite high equilibrium values here. These actually are quite soluble when they have those ligands present. They're pretty happy to go into solution if they have their little ligand buddies with them. So the last thing here that I want to discuss is just very generally how we can use the solubility of molecules to actually help us with qualitative investigations. If we're trying to figure out, for example, we work at an oil company and somebody digs up some kind of solution and they suspect that there's something not good in the water that's coming up from the drill site, and they send you a sample of that water, you can do a process similar to this to try and work out what is in this solution, what metals are present here. So you could start by adding, for example here, some HCl. If you add 6 molar HCl and you get a precipitate, it's most likely one of these three things. It's either silver chloride, lead chloride, or mercury chloride. If it's either of those two, it's probably bad news. If you have silver coming up from your drill, ooh, that's probably good. Call the presses. If you don't get anything, so no precipitates from that first one, you can take what you have left and add some sulfur to it, specifically H2S, with a little bit of HCl as well. And if you get a precipitate there, it's one of these. And you can just kind of keep working your way down the tree here, so to speak, and eventually you will be able to work out within a few ions what you actually have in your mixture, and then you can go on to other methods for testing from that point forward. But this is a relatively common way to qualitatively, at least, you don't actually get concentrations or anything, but just qualitatively figuring out I probably have, iron, chromium, zinc, nickel, manganese, cobalt, or aluminum. It's like, well, that's a lot of possibilities. Well, yeah, but that's a lot fewer than everything on the periodic table. So it still does leave you with some investigating to do, but it does narrow down the possibilities quite a bit. All right, that is it for this one. I will see you all in the next chapter of slides.